So this is the presentation for SLAM and path planning. So this is what a navigation stack in ROS would look like. It consists of several nodes, and has each node has its own specific purpose. So for so the first job we need to do is to generate a map of our environment. So it's basically like a 2D occupancy map. So if there's an obstacle or like a wall here or here, so this black or like red lines here would tell the mobile robot that it would tell the mobile robot that these lines here are not occupiable. So the mobile robot will take these black lines as no-go zones. So this kind of occupancy map is generated by the map server, and it also saves it. So the map server will use the LiDAR information, and it probably uses Hector SLAM. We can use any other SLAM algorithm, but since we don't have wheels, we only have one sensor, so which is the LiDAR. Hector SLAM is a good alternative. Another one is like called G mapping. However, that requires wheel encoder, and we don't have wheel encoder, so I guess Hector SLAM can be useful for us. It's already coded, and so we do not have to do much about that. And then this is for localization. So this node will take the map information from here, and then it will use the map information and the sensor information, in our case the LiDAR information, to localize itself on the map. So this AMCL node, also called as the Adaptive Monte Carlo Localization node, is responsible for localization. And in order to use our LiDAR sensor, we will need to somehow convert the sensor information into meaningful data. So that's done by sensor sources. So usually we need to program this for our specific sensor, but since the RP LiDAR is quite ubiquitous, there's already a pre-written package, so we do not have to do much work for this. So this is already done for us by ROS, and then the sensor transformation will give us the relative transformation between the sensors and the base of the vehicle. So for example, say if our car is here, and if this is our base link and our sensor is here, it will basically tell the car or tell our system the relative transformation between these two. This needs to be set up by us, and there are ways to easily do it by using the URDF of our mobile system model, mobile robot model. So URDF is basically a way to represent a model in gazebo simulation, I believe. And I believe we can also generate a URDF from a CAD file. So I guess this could be quite straightforward as well. This could be a little bit of an issue. So usually odometry. So what's odometry? Odometry tells us the current estimate of the current position and velocity of the car. So that, and with conjunction with the AMCL, we can find the current location, the current speed of the car quite well. Usually the wheel encoder information is used to get an estimate of the velocity and the current pose. But since we don't have wheels here, I guess we can use cameras and an IMU sensor to do a visual inertial odometry thing. So that could be useful. There are some algorithms called Vince Fusion, which uses camera and then IMU sensor to basically estimate the pose of the vehicle. So yeah, this we need to do more research on this part, and then given all this information, this node here will generate the path or the trajectory. For path planning, there is two main parts: global planning and local planning. So global planning is, so for example, say this is my start and this is my end. Global planner will find the shortest route like this. It does not take into account of any of the dynamic obstacles. So in real world's case, there could be a car swerving in or an obstacle, something like that. Global planner does not do that. It takes the occupancy grid map from here, and then it basically generates the shortest path between the goal and the ending point using some kind of algorithm such as A-star, Dijkstra. This is already done for us by Ross, so yeah, we don't have to do much either here. And local planner is basically the real-time obstacle avoidance detection, stuff like that. So for example, if in real world there's an obstacle here, the car comes here, says that there's an obstacle here, it will generate an alternate trajectory like this and then go here. So this is basically what local planner does. So these are already done for us by Ross. We do not have to think about it. This could be an issue. So if we were using a differential drive car, differential drive means there's two wheel with independent motors. Or if we are using drones, it's that kind of control system is quite common. So we would have a lot of stuff online that we could just copy. But since our control system is a little bit novel, we need to find a control model for our case. So usually in order to find the model, we need to derive the equation of motion. So for example, like we need to derive stuff like this, where this is the control input, this is the current state, the change or rate of change of state, and this is the current state. And usually we use this to control our car. And deriving this equation of motion is kind of tedious. For a previous course, I derived it for a differential drive car. It's quite a simple system. It was a little bit tedious, so I guess in our case it would be even more difficult. So I was checking of a way to easily model the car, model our hovercraft, and I found this thing called Sim Mechanics in MATLAB. Sim Mechanics is built on top of Simulink, so it can be used to find the model of the system without us explicitly deriving the equation. So we can import the CAD file from SolidWorks and it will automatically generate something like this for us. It will give us all the relative transformation and then all this stuff, and then we can use our CAD model in here to simulate it. And so basically we can test and simulate our control algorithm on MATLAB before even implementing it real world. So I need to check a little bit more on that. I do not completely understand right now how to use it. So I think this could be a good way for us to go forward. So yeah, that's my part for today's presentation. Thank you.